We're used to seeing the cosmos as infinite, impenetrable darkness, pierced by rare rays of lonely stars. However, the vast expanse of the universe hides a splendor that can hardly be imagined on Earth. The crimson shimmer of nebulae, the bright blue brilliance of giant stars, and the burning ultraviolet glow of quasars combine to form an incredible multicolored palette. And today, we're going on an amazing journey through it. Our journey begins near the Orion Nebula, then we'll fly along the glittering arms of the Milky Way, through dazzling star clusters and mysterious dust clouds. Next, we'll travel through the chilling vacuum to the magnificent Andromeda Galaxy and cross the dark and mysterious chasms of giant voids, those great rifts in space. Eventually, we will look around the cosmos to see how the immutable laws of nature are woven into the great chaos that governs the universe. Let's get ready, and we begin. There are stellar nurseries richly scattered across the galaxy, with some of them comparatively modest in size. Others stretch for tens and even hundreds of light years. These are vast nebulae made up of interstellar gas and dust being inexorably compressed by gravity forces. Most of these tremendous clouds are barely visible against the abyss of space, but some of them can be seen from the Earth with the naked eye. One of these structures is the Orion Nebula, located 1,344 light-years away from the Earth. It is the middle object in the so-called Sword of Orion, a clearly visible line produced by three relatively bright light sources. Due to its large size and comparative closeness to the Earth, the nebula has been attractive for scientists ever since the early days of astronomy. It is hardly surprising, therefore, that this great structure is one of the best-studied space objects. It was the Hubble Orbital Space Telescope that beamed back first images of the Orion Nebula back in 1993, where the rich diversity of its colors can be appreciated. Most of the material was of a reddish or bluish-purple hue, while unusual bright green lines of some peripheral areas were revealed by spectral analysis. This phenomenon perplexed scientists for a long time, as the observed radiation did not demonstrate any chemical element known at the time. There was even a hypothesis that was put forward about there being a hypothetical element, nebulium, argued to be not present on our planet, but allegedly amply scattered across clouds and space. However, with the advancement of science, it turned out that the light was emitted by extremely rarefied and deionized oxygen. This discovery accounted not only for the bizarre illumination of many nebulae, including our Sun. There are currently not less than 3,000 stars discovered in the Orion Nebula to date, as well as giant clouds of interstellar gas and a great number of protostars. All this amazing diversity of space objects is concentrated in an area of around 23 light-years in diameter, all of them continuously and elaborately interacting with each other. The overall mass of the material concentrated here is around 10,000 solar masses. Looking at the Orion Nebula closer, we will notice several clearly defined areas. The most outstanding of them is trapezium, also known as Theta 1 Orionis. It's an open star cluster about 300,000 years of age, made up of 8 main components. Some of them are binary stars, others have no companions. The brightest and most noticeable of the trapezium stars are 4 stellar systems designated by letters of the Latin alphabet. Located close to each other, they lie within an area about 1.5 light-years in diameter. Each of these objects' mass is within 15 to 40 solar masses, which means that these stars are quite young and hot. Theta 1 Orionis C is the most massive, as well as the brightest star in both the trapezium cluster and actually the entire nebula. It is a white and blue main sequence star with a mass roughly 40 solar masses, whose radius is 8 times that of the Sun. The object's surface temperature is approximately 45,000 Kelvin, and its luminosity about 250,000 times higher than that of the Sun. The radiation of Theta 1 Orionis C illumines virtually all the nebula around it, but there is hardly any interstellar gas in its immediate vicinity. This is the case due to the fact it is typical for objects of this class to experience exceptionally powerful stellar wind that scatters rarefied material far off. Having traveled a few light years away from Trapezium, we will see another remarkable system, which is Theta 2 Orionis. It is made up of 3 gravitationally bound stars located close to the so-called Orion bar, an extensive feature of hot gas emitting bright light. It was impossible to study this area for a long time on account of dense clouds of dust, and thanks to the James Webb Telescope, more detailed images of this region have been beamed back to us. The first component of Theta 2 Orionis is just slightly less massive and not as luminous as the Trapezium's biggest star. As for its surface temperature, it measures about 35,000 Kelvin. The second component of the system is 15 times as massive as the Sun and 12,000 times as bright. The third component is as heavy as 5 solar masses, and its temperature almost reaches 14,000 Kelvin. However, it wasn't just bright stars that caught the researchers' attention. James Webb's infrared cameras allowed it to detect previously unseen objects, hidden deep within the clouds of gas and dust. Thanks to the telescope, about 180 so-called proplids have been discovered at the heart of the Orion Nebula. These are dense, dark protoplanetary disks surrounding stars that are still in the process of formation. One of these is Orion 294-606, a young protostar about 1 million years old, surrounded by a gas and dust disk about 300 astronomical units in diameter. Thanks to its being edge-on to Earth, we can observe its structure and size. It is expected to hit the main sequence phase in a few million years, and it will be accompanied by a system of several exoplanets and possibly their satellites. The night sky of these future celestial bodies must be a truly fantastic sight. Just imagine a multicolored luminous veil with the glow of a multitude of close and bright stars far more numerous than those seen from the Earth coming through. And now and then tremendous swirls of glowing gas cover half the sky, turning the night into translucent twilight. If we fly a little further and examine the wider region, we see that the bulk of the nebula is filled with scattered gas. The central part of the cloud is filled with highly ionized hydrogen, which actively absorbs high-energy stellar radiation. The temperature of this gas can reach 10,000 Kelvin, but it falls sharply towards the edge of the region. Temperature and pressure contrasts, as well as the collision of stellar wind streams, set material in space in motion, creating tremendous currents and vortices. According to calculations, some of them can reach speeds of up to 50 kilometers per second, and their size can be greater than the solar system. Also, in some areas of the nebula, thin strands stretching for several light years have been detected, consisting of relatively cool molecular hydrogen, without mixtures of methane, ethane, and water. Further out, we will see that the central region of the Orion Nebula is enveloped in a vast cloud of cooler, denser gas. The cloud of bright stars and the luminescence of ionized hydrogen intricately intertwine here, creating a beautiful multicolored curtain of light. Hidden behind it are hundreds of space objects, invisible in the optical range. But the infrared cameras of today's telescopes allow us to see through the veil of interstellar matter. By combining data from different sources, astronomers have discovered about 700 protostars at different stages of evolution within this region. Their concentration is noticeably lower than in the central part of the nebula due to the lower degree of gravitational compression of the interstellar gas. The absolute majority of these objects are very young by space standards and are still in the process of formation. According to modern concepts of stellar evolution, new stars form during gradual gravitational compression of large clouds of interstellar gas. Typically, as a result of this process, giant nebulae split up into a number of closely grouped gravity centers, which soon turn into protostars. Such clusters are called stellar nurseries, or more scientifically, regions of star formation. At a certain point, the internal pressure of the compressed gas compensates for the gravitational forces, bringing the protostar to a state of temporary equilibrium. The remaining material swirls into a giant vortex disk, with some of it gradually absorbed by the future star, and the rest of it, by contrast, expelled far beyond the boundaries of the nascent system. The growing magnetic field of the young star also plays its part. As ionized particles accelerate through its field lines and then rapidly escape from the vicinity of the object, it has been calculated that such flows can reach speeds of up to several hundred kilometers per second. As they collide with the gas clouds surrounding them, they create large-scale vortices and hemispheres called Herbig-Haro objects. In the process, part of the kinetic energy dissipates into light and heat, giving these bizarre structures different colors. In addition, the ultra-fast motion affects the surrounding material, spreading shockwaves across it, which incidentally are also captured by telescopes. Since stellar nurseries contain many closely spaced protostars, each producing several gas emissions, it is not surprising that Herbig-Haro objects exhibit an amazing variety of shapes and colors. Clearly, being essentially the result of a major cosmic collision, they are highly unstable and variable. Herbig-Haro objects rapidly change color and shape, and typically disperse completely over several tens of thousands of years. During this time, they cover between 1 and 3 light-years on an escape trajectory from their parent stars. About 400 such objects have been discovered so far, with their total number within the Milky Way estimated to be about 150,000. Perhaps one of the varieties of this awe-inspiring natural phenomenon is the bullets, hundreds of astronomical units in diameter, also detected in the Orion Nebula. Moving at incredible speeds, they easily pierce thinner hydrogen clouds, creating far-flung shockwaves in them. According to spectral analysis, the frontal parts of these objects contain atoms of iron that glow in the infrared. The bullets are estimated to be about 1,000 years old, and their origin is still a mystery. They supposedly originated from some catastrophic event. Moving on, we will soon find that the Orion Nebula is part of a much larger cosmic structure called the Orion Cloud. It stretches for hundreds of light-years, accounting for virtually the entire constellation of Orion in the Earth's night sky. This is where the well-known Horsehead Nebula is located, remarkable for its bizarre shape. It is a dense dust cloud, about 3.5 light-years in diameter, clearly visible against a background of a contrasting scarlet glow. Also close to the Orion Nebula, there is an impressive cosmic structure called the Barnard's Loop. This emission nebula, about 300 light-years in size, came into being about 3 million years ago, after a series of consecutive explosions of mutually close supernovae. After the shock-compressed gas jets mixed together, they produced a gigantic curved nebula, and the glow of several young stars, gathered in an open cluster, made it reddish in hue. For all its beauty, the Orion Nebula is a fragile and unstable object by the universe's standards. Stellar winds and pressure of light from many young stars, as well as gas emissions and turbulent vortices, constantly disperse its material in the surrounding space. The nebula has already lost about 60% of its original material, and in about 100,000 years, it will be stripped of its remnants. In place of the shining multicolored cloud, there will remain an open star cluster similar to the Pleiades. For a time, the young stars forming it will move together, but eventually, each will find its separate way through the vast expanse of the boundless galaxy around. Long before telescopes had been invented, people could observe a light strip crossing the heavens. The fascinating and mysterious phenomenon prompted a multitude of legends, but it took thousands of years of scientific progress to finally account for it. It turned out that the Milky Way wasn't a path of gods. What it is the dissipated light of billions of stars too remote to distinguish each one separately. The idea of the stars around us making up part of a single structure of enormous dimensions was first suggested by Immanuel Kant back in 1755. He also assumed that some nebulae discovered by scientists could in fact be remote star clusters, that is, other galaxies. This ingenious guess was well ahead of its time, with the philosopher's contemporaries initially dismissing it. Only in the early 20th century did the progress of observation equipment enable scientists to confirm the existence of other galaxies, and in 1936, Edwin Hubble devised a classification system. Many of its principles are still referred to by scientists today. According to this system, the Milky Way falls into the category of barred spiral galaxies, although it took a long while before it had assumed its today's looks. Our galaxy is quite an old one, since the stars in its central globular clusters were born as far back as around 13 billion years ago. At the same time, there are some areas in the Milky Way where stars are actively born, which means that there is always a fresh supply of young stars. The collected data points to the fact that the Milky Way is a comparatively large galaxy in astronomical terms. The diameter of its disk measures as much as 200,000 light-years, with a halo reaching out into space much deeper yet. Our galaxy is home to at least 200 billion various stars, as well as 25 to 100 billion brown dwarfs. In addition, it contains over 1 trillion planets, countless small celestial objects, as well as clouds of cosmic dust and interstellar gas, which may reach gigantic dimensions. At the same time, regular matter accounts for a small ratio in the galaxy. Around 90% of the Milky Way's overall mass is the so-called dark matter. The amount of light emitted by this mysterious and widespread substance is negligible. However, dark matter plays an active role in gravitational interaction. Even though most of the galactic mass remains invisible, we can still calculate it. To that end, scientists refer to stars' trajectories of movement around the center of the Milky Way. According to the estimates, the overall mass of our galaxy reaches 0.8 to 1.5 trillion solar masses. The structure of the Milky Way is quite elaborate. We'll start our journey today from its center. This area of the galaxy is shrouded in massive clouds of gas and dust, but by happy chance we can observe it through the so-called Bardes window, an area of space with lower amounts of dust. Just like most spiral galaxies, the Milky Way has a supermassive black hole in its center, which is surrounded with an accretion disk with a radius roughly 3 light-years. Dubbed Sagittarius A star, it is the closest object of this class to us. Its mass is 4.3 million solar masses, and its radius isn't over 16 million kilometers, which is 3 times smaller than Mercury's orbit. The first data about the nature of the object in the center of our galaxy was acquired in the course of long observations and thorough calculations. Only as recently as on May 12, 2022 was it possible to get the first image with the help of the EHT network of radio telescopes, and so the earlier hypotheses were confirmed. The area in the center of our galaxy is highly populated. More than 6,000 stars have already been detected within 3 light-years from the black hole, with the orbits of some of them defined rather accurately. For example, there is a white-blue star, designation S62, which is 17.8 astronomical units away from the black hole on its closest approach to it, while moving at 6.7% the speed of light. Classical mechanics laws are inadequate for description of the trajectory of movement of a star as swift as that because of relativistic effects. Just to illustrate, the axis of its orbit shifts by 75 angular minutes with every completed orbit. Besides, when crossing this area in space, we can see several large star clusters with a total mass of around 1 million solar masses. And slightly further, roughly 200 light-years away, another massive black hole is likely to be lurking, whose mass should be around 100,000 times that of the Sun. Traveling further on, we will reach the central molecular cloud, an irregularly shaped area measuring 1600 to 1900 light-years, whose mass is over 60 million solar masses. There are a great many stellar nurseries and gas nebulae, as well as protostars and remnants of supernovae. Most of the cloud's matter is dense hydrogen, whose temperature fluctuates between 50 and 600 Kelvin, which corresponds to 223 degrees Celsius below zero to 327 degrees Celsius above zero. Spectral analysis shows the gigantic nebula to contain carbon monoxide, methyl alcohol, and hydrocyanic acid in addition to hydrogen. Having receded from the Milky Way's center a bit, we will see that it is encompassed by a bulge, a bright and massive formation of an elliptical shape. With its length reaching 10,000 light-years, its transverse diameter is roughly 7 light-years. The total mass of the bulge is as much as 10 billion times that of the Sun. The exact number of the stars cannot be calculated because their radiation blends and renders any estimates unrealistic. Being elongated, the bulge forms the so-called bar stretching for approximately 13,000 light-years and serving as the base for spiral galactic arms. It is here, at one of its ends, that we can see the star cluster Stephenson 2, containing the largest known star today. Its designation is Stephenson 2-18, and its radius is 2,150 times that of the Sun. Unfortunately, chances of finding exoplanets orbiting this outstanding object are quite minuscule. Even if planets did exist at some point in the past, the hypergiant would have swallowed them up while it was expanding. The galaxy's center is home to billions of stars and apparently a great number of exoplanets. Chances of encountering a potentially habitable world among this great multitude are much lower than in less populated areas of the galaxy. This is due to the fact that when a big number of stars are located close together, they destabilize exoplanets' orbits, while their powerful radiation is lethal to all living things. That is why a special area in the galaxy is defined as the habitable zone. It looks like a ring, with a radius measuring 22 to 29,000 light-years, and contains star systems with the most favorable conditions for the genesis of biological life. Worlds encompassed by the ring languish in exposure to excessive radiation, while beyond the ring there's a lack of heavy elements. However, mathematical modeling shows that stars within galaxies are able to migrate thousands of light-years away, thus either leaving the habitable zone or entering it. Consequently, with an exoplanet lying within the zone, it does not automatically suggest favorable conditions on it. Moving on away from the center of the Milky Way, we will have a chance to check out its most impressive part, the galactic disk. It is made up of two components with different properties. The first one, known as the thin disk, measures 1,000 to 1,300 light-years in thickness, and its visible radius measures as much as 50,000 light-years. On the edge, it gradually dissipates, with the outermost stars lying up to 100,000 light-years away from the galaxy's center. This part of the Milky Way contains around 80% of the galaxy's visible mass, and in fact, it was the last component to have formed. As for the thick disk, its diameter is comparable to that of the thin disk, but it's 4 times as thick and is much more rarefied. It is made up of old stars and is practically devoid of interstellar gas. Observations of some stars in the Milky Way, as well as mathematical modeling, show our galaxy to have swallowed up another one in the period from 11 to 8 billion years ago. This hypothetical cosmic structure was dubbed Gaia Enceladus. It is thought that it contributed several billion stars to the Milky Way, as well as great amounts of interstellar gas and dark matter. It is thanks to this tremendous event that most of our galaxy's thick disk formed, and an additional supply of gas led to a stellar baby boom. There is no doubt that spiral arms are the most noticeable structural elements of our galaxy's disk. Usually two major ones are singled out, the Scutum Centaurus arm and the Perseus arm, and two minor ones, the Norma arm and the Carina Sagittarius arm. Sometimes a fifth large arm is taken into account, named after the Cygnus constellation. Galactic arms are areas of especially high star count. Most of interstellar gas is also concentrated here, which is why the rate of star formation in the arms is 3 to 5 times higher than in the galaxy on average. They spend the first millions of their lives in open clusters, but gravity forces are too weak to hold the stars close together for a long time. This destabilizes the clusters, and young stars gradually drift away from each other. Traveling along the Carina Sagittarius arm, we will reach a fork that links it to the Perseus arm. The length of this stellar structure reaches 11,000 light-years, and its width measures roughly 3,500 light-years. It is referred to as the Orion arm, and it is here, 27,000 light-years away from the galaxy's center, that the solar system is located. From our planet's perspective, the galaxy's center is seen as a dark abyss. This is the Great Rift, an area of space that shuts out the greater part of the Milky Way from our gaze. It is filled with massive clouds of interstellar gas and dust, and its total mass is as much as 1,000,000 times that of the Sun. Even though the Great Rift is practically not transparent in the optical range, its matter actively emits radio waves and thermal energy. Spectral analysis data reveals that the clouds are mostly made up of hydrogen with a small percentage of more complex compounds, ammonia, alcohols, and amino acids. The Great Rift is thought to be a potential stellar nursery, but it is going to take a while until the first stars light up in that area. While it is still not quite active, let's move on, beyond the galaxy disk. Even though its bright and clearly defined arms attract a lot of attention, there is more to the Milky Way than that. If we look closer, we will see the vastest and the most rarefied of its components, the halo. Its visible part, spherical in shape, stretches for up to 260,000 light-years away from the galaxy's center, but accounts for just a few % of the total mass. The halo contains a great number of globular clusters made up of remarkably old stars over 12 billion years of age and several tremendous stellar streams. The Sagittarius stream, for example, made up of several thousand stars, encompasses our galaxy in an elongated ellipsis, which is almost perpendicular to the main plane. Modeling shows that all these stars are highly likely to have been gravitationally captured by the Milky Way from a dwarf satellite galaxy. Designation Sagittarius DEG. It lies 500,000 light-years away from the Milky Way's center and is going to be swallowed up by it completely within several billion years. Another dwarf galaxy has already met a similar fate. Lying in the Canis Major constellation, it was almost destroyed by the Milky Way, which pulled out millions of its stars by gravity forces. Stretching for 200,000 light-years and mixing with other stars, this string of stars with a total mass of roughly 100 million solar masses has already wrapped around our galaxy 3 times. Apart from bright but rare stars and clusters, the halo contains great amounts of gas, whose temperature reaches millions of Kelvin. Also, great amounts of dark matter are thought to be scattered in the vicinity of the Milky Way, forming the so-called dark halo. Stretching for up to 2 million light-years, it hardly emits any electromagnetic radiation and can be detected only by gravitational interaction. The dark halo remains an unsolved mystery, yet it greatly contributes to the global stability of our galaxy. $2,500,000 years ago, the Andromeda Galaxy. a giant star expires close to the galactic core. The last seconds of its life pass in an explosion of tremendous force. Trillions of tons of red-hot plasma explode in a huge cloud, turning the nearest planets and satellites to dust. A powerful electromagnetic impulse pierces outer space in all directions. Millions of years later, it is to reach the Earth. The year 1885. The planet Earth. The attention of all astronomers on the planet is focused on an amazing astronomical event. A remarkably bright flare in the region of the Andromeda Nebula briefly eclipses the nearest stars with its radiance. This amazing supernova is dubbed as Andromeda, and its anomalous parameters baffle astronomers for a long time. But just 6 months later, the star rapidly dims and soon disappears from the sky forever. Unfortunately, at the time of the flare, generally accepted notions about the structure of the universe were far from those of today. At that time, astronomers were not yet able to measure distances to cosmic bodies, so the bright spot in the constellation Andromeda, also known as object M31, was considered an ordinary reflection nebula on the outskirts of the Milky Way. Meanwhile, with the advent of new, more powerful telescopes and the development of space technology, the situation gradually changed. As soon as in the 1920s, observations by Edwin Hubble and other astronomers proved that the Andromeda Nebula is a different galaxy, much like the Milky Way. About a century has passed since then, and science has moved far ahead. It is currently known that the Andromeda Galaxy has a spiral structure and comprises about 1 trillion stars. As for its diameter, it exceeds 150,000 light-years, and its mass is relatively small and ranges from 800 billion to 1.5 trillion solar masses, about the same as the Milky Way. This is thought to be the case due to the abundance of red dwarfs and less dark matter in its composition. Like all spiral galaxies, Andromeda has a massive nucleus at its center, made up of millions of closely spaced stars. Its radiance is so great that it dazzles observation instruments, making it impossible to distinguish individual stars. On account of this, the remnants of the 1885 supernova, known as S Andromeda, have long been impossible to trace, although surviving records clearly indicate that it exploded near the center of the galaxy. It was only in 1988, 103 years after the legendary flare, that a small nebula was detected at a small distance from the nucleus, a dark spot standing out against the background of the dazzling central region. With the help of spectral analysis and proper motion modeling, it was firmly established that it is a remnant of S Andromeda. Thus, this cosmic object became the first supernova detected outside the Milky Way. Careful study of the central part of Andromeda will clearly reveal its unique difference from other spiral galaxies. It is an unusual double nucleus, the origin of which is not yet fully understood. The brighter and larger part is located slightly away from the geometric center of the galaxy and is a giant supercluster of many bright stars with a total size of about 7 light-years. The second part, on the other hand, is closer to the center and is noticeably dimmer and smaller, with a diameter of about 1.3 light-years. It is assumed that this region hides inside a supermassive black hole about 50 million times heavier than the Sun. The nature of such a strange phenomenon remains a subject of scientific debate. According to some assumptions, in the distant past, M31 absorbed and scattered a rather large satellite galaxy, and the bright region is a remnant of its core. According to other hypotheses, the center of Andromeda still has a single structure. However, it is separated by a band of opaque dust, creating an unusual optical effect. Due to the remoteness and inconvenient location of the galaxy in space, it is still impossible to collect enough data to confirm these hypotheses one way or another. Meanwhile, as we continue traveling through the central region of Andromeda, you can also spot one of the most mysterious objects in this galaxy. Here is its tongue-twisting name on your screens. The key feature of this celestial body is that it is almost impossible to see even in the most powerful optical telescope. However, everything changes if you use X-rays. In this part of the spectrum, this star is the brightest point in the galaxy. Observations show that the object is a system made up of two components, one of which is a low-mass neutron star. Its radius is only a few dozen kilometers, and it completes a full turn around its axis roughly every 3 seconds. The second star of the system is a larger object. Although it is relatively dim, it's most likely a red giant. Calculations show that the total mass of both components is not more than 3 solar masses, and the distance between them is very small. Every 4 hours, the neutron star is eclipsed by the other star, and this causes its luminosity to sharply drop, to recover its previous values later. It is also very likely that due to the small distance between the stars, the neutron star is gradually absorbing its companion, which is why its mass is constantly growing. According to calculations, this process will last several tens of millions of years, and eventually, the second star will be torn apart by tidal forces and turn into a bright and hot ring-like nebula. Incidentally, this amazing object is only one of the many stars densely surrounding Andromeda's core. Together, they form a massive bulge with a diameter of about 12,000 light-years, which has a noticeably elongated shape. Also, M31 has a pronounced bar, which however faces us with its narrow side and so is almost invisible to the observer on the Earth. According to calculations, the bar's length measures about 17,000 light-years, with a width about 6,500 light-years. In total, about 30% of the Andromeda Galaxy's entire mass is concentrated in its central part. While we are gradually moving away, we can see that the edges of the bar serve as the basis for 2 giant spiral arms, majestic coils encompassing the center of the galaxy. At the same time, there are darker gaps between them, whose width is significantly larger than those in the Milky Way, reaching 13,000 light-years. Calculations show that the Andromeda arms contain about 56% of the galaxy's stellar mass, as well as some dark matter. Under the influence of gravity, interstellar dust and gas concentrate in the arms, forming numerous stellar nurseries, regions where new stars are born. Over time, these gas and dust clouds evolve into open clusters and associations containing a great variety of young stars. Their light is reflected and scattered by cosmic nebulae, endowing the galactic disk with an incredible, shimmering palette of colors. And in one of these clusters, there is a remarkable star dubbed AE Andromeda. It is one of the brightest stars in the galaxy and is a hot blue giant whose luminosity varies without any apparent pattern. Such objects are known as luminous blue variables and are extremely rare. Currently, only a few dozen are known. Because of the extremely high temperature and pressure, the outer layers of AE Andromeda are constantly in a state of unstable equilibrium. and the processes running in the interior of the star are largely chaotic and unpredictable. From time to time, streams of red-hot plasma collide with each other, generating extremely bright flares and enhancing the luminosity of the object by several dozen times. Hypothetically, the most powerful of them can increase the brightness of the star several million times. Such a phenomenon is called a supernova imposter and may occur at any time. Measuring the parameters of such a star, what with its instability and remote location, is an extremely difficult task. Nevertheless, with the help of modern ultra-precise telescopes, it turned out that the mass of A Andromeda lies in the range from 50 to 120 solar masses, and the radius at the peak of pulsations measures about 55 times the radius of our Sun, which is only slightly smaller than the orbit of Mercury. At the same time, its surface temperature is close to 20,000 Kelvin, and its luminosity is 500 to 700,000 times greater than that of the Sun. Just like all blue giants, A Andromeda generates remarkably strong stellar wind, whose speed, according to calculations, can reach 100 kilometers per second. Because of this, the object loses about 2 quadrillion tons of matter per second, which means that its mass decreases annually by an amount similar to 10 planets such as Earth. However, for such a large star, it is almost imperceptible, because A Andromeda will complete its evolution much sooner than the losses incurred from the stellar wind will reach at least 0.1% of its mass. The fact is that despite its age of 2 million years, which is mere seconds by space standards, A Andromeda has already completed most of its life cycle. According to calculations, within the next million years, the star will go supernova, leaving behind a black hole surrounded by a vast gas and dust nebula. Speaking about the age of the stars, one cannot help noticing that they are scattered unevenly throughout the galaxy. Thus we can look into Andromeda's past and observe how it was being formed. The oldest stars, some 11 to 13 billion years old, are concentrated in the central part of the galaxy. In contrast, the disk and spiral arms mostly contain younger stars, ones formed about 3 to 4 billion years ago. Here, the numerous stellar nurseries contain pretty much baby stars, born only a few million years ago, which is practically seconds by space standards. This means that in the first stage of its evolution, M31 was much smaller in size, and its shape resembled an ellipse. Also, by analyzing the parameters of individual stars in Andromeda, it is possible to define an important, but at the same time rather conditional concept known as galactic habitable zone. It is believed that the concentration of stars in the central part of Andromeda, as well as the high level of radiation and unstable orbits of potential exoplanets, make this zone unfavorable for the genesis of life. At the same time, distant planetary systems located at the periphery of the galaxy are too poor in heavy elements, which implies that there are not that many Earth-like planets. Therefore, only the intermediate region of the galaxy can be considered hypothetically habitable. It is in this kind of zone, at a distance of about several tens of thousands of light-years from the center of the galaxy, that a small faint object known as Mega ML7 is located. It is a red giant, with a relatively small mass of about 50% that of the Sun. In 1999, thanks to a fortunate coincidence, astronomers were able to record the phenomenon of microlensing, during which they were able to study this inconspicuous and distant space body in more detail. The results of these measurements helped determine the mass and spectrum of the star, as well as the temperature of its surface, which was about 3,700 Kelvin. But the most important observation was the rhythmic deviation of the trajectory of the star from the main direction of its movement. Such oscillations are considered a sign of a possible presence of a fairly massive companion. The hypothetical object was dubbed Mega ML7b, and is now considered a potential exoplanet. If the existence of this celestial body is confirmed, it will be the first exoplanet in the history of astronomy to be discovered outside the Milky Way. Information about this object is still rather scant, but calculations show that it is highly likely to be a gas giant, with a mass of about 6.3 times that of Jupiter. There are also reports that this system is likely to be as diverse as our own in terms of chemical elements, which means that there is a good chance of finding a variety of planet types within its boundaries. Not only gas giants, but also rocky celestial bodies similar to Earth. When we observe the Andromeda Galaxy, another striking feature that becomes immediately apparent is the great multitude of star clusters and associations, whose number is much bigger than in the Milky Way. In total, about 460 globular star clusters and about 10,000 open clusters are known to exist in M31, as well as several dozen large star associations. Some of them are concentrated in the center of the galaxy, others are scattered in a halo, and still other ones have settled right in its spiral arms. And one of the largest and most noticeable structures is NGC 206, a cluster located almost at the very edge of the galactic disk. Previously, this association was considered a globular cluster, but now, due to its size, it has received a higher status and is called a stellar association. In this region of space, with a radius of about 200 light-years, roughly 300 extremely bright stars and countless less noticeable ones are concentrated, with a total mass of about 200,000 solar masses. Their overall luminosity is so great that the association is visible from Earth in an amateur telescope, along with the core and arms of the galaxy. According to observations, NGC 206 formed after a merger of at least two large gas and dust nebulae separated by a dark band of interstellar dust. The age of one of them is about 10 million years. The other is noticeably older, having formed about 50 million years ago. The single giant nebula became a point of gravitational attraction for interstellar gas, which led to the formation of a great area of star formation. Over time, some of its stars will dissipate in the surrounding space, with the rest forming a large globular cluster. The galactic disk M31 contains many such formations, and not all of them originally formed within its boundaries. It is assumed that many large stellar associations are the remnants of major cosmic catastrophes of the past. According to calculations, throughout its entire existence, Andromeda absorbed more than 100 satellite galaxies. Some of them dissolved without a trace, while others turned into giant stellar streams. The collision with the object known to us as M32 may be considered the greatest. This compact elliptical galaxy is located above the Andromeda disk, only 17,000 light-years away from it. Its diameter is about 8,000 light-years, and considering its small size, the galaxy has a rather big mass, about 1 billion solar masses. In the center of M32, there is a supermassive black hole about 2.5 million times heavier than our star, which is surprising for such a compact object. In fact, M32 is just a remnant of a much larger galaxy that survived the Great Catastrophe. According to data from the Spitzer orbiting telescope, about 800 million years ago, a large satellite galaxy pierced Andromeda's disk at high speed, leaving a gigantic hole in one of the spiral arms. During this collision, M32 lost most of its stars, and it is unlikely to be restored to its former appearance. It is assumed that it could have been a full elliptical galaxy, or a small spiral galaxy, of which only the central part remains. In addition to M32, Andromeda has about 30 satellite galaxies connected to it by invisible gravitational threads. The brightest and largest of them is M110, which has a diameter of about 15,000 light-years. Most of the rest fall into the category of dwarf spherical galaxies and are located within 1,000,000 light-years. Nevertheless, together they form the Andromeda subgroup, which is part of the local group. Its other members are the Milky Way and its surroundings, as well as the Triangulum Galaxy and some other objects. Inexorable gravitational forces are gradually pulling the local group towards a single center. That is why the Andromeda Galaxy is rapidly moving in our direction, covering over 300 kilometers every second. In terms of the vastness of the cosmos, our planet is just a small rocky fragment traveling at incredible speed through boundless emptiness. For billions of years, it has been orbiting the Sun, maintaining a distance of about 150 million kilometers. However, the true size of our system is much larger. According to modern concepts, its outer boundary, which is considered the far edge of the hypothetical Oort cloud, is at a distance of about 100,000 astronomical units. Beyond this boundary begins the vast abyss of the interstellar vacuum, space so rarefied that there is on average only a single hydrogen atom per cubic centimeter. The distances between the nearest stars in our part of the galaxy are a matter of a few light-years, and a photon that has left the Sun can reach Proxima Centauri without ever colliding with a particle of matter. This vast void is a pervasive and integral part of the deep structure of the cosmos. It permeates the entire Milky Way, separating stars and planets, black holes and white dwarfs, super-dense pulsars and scattered nebulae. If you move outside the galaxy, you can see that it is surrounded by an even deeper vacuum. For example, between us and the Andromeda Galaxy lies 2.5 million light-years of exceptionally rarefied space. This distance is so great that 25 galaxies like ours could fit in it, yet it is filled only with the deepest cosmic vacuum. And this is only a small part of the great cosmic abyss. The Milky Way, the Andromeda Nebula and the Triangulum Galaxy, as well as about 100 of their satellites, are bound together by pervasive invisible threads of gravity. This structure is called the local group and is a large cluster of cosmic matter about 10 million light-years in diameter. The local group, in its turn, is part of an even larger formation, but a relatively small galactic filament by the standards of the universe, called the local sheet. This flattened structure, consisting of several hundred galaxies, has a diameter of about 46 million light-years, and its thickness is roughly 5 million light-years. The sheet is also part of an even larger association called the Virgo supercluster. However, very close to the local sheet, outer space suddenly changes its appearance. Here, the usual colorful universe is harassed by a giant black abyss known as the local void. In fact, the local sheet is one of its walls, the other conventional boundaries being the Perseus-Pisces supercluster and the Pavo-Indus supercluster. At the same time, the void is divided into conventional parts by several rarefied galactic filaments, and wide passages link it into a single network with the neighboring Sculptor and Hercules voids. Due to the cosmological expansion of the universe and the gravitational influence of the surrounding matter, the volume of the local void is slowly increasing. At present, its diameter is about 150 million light-years, and the distance to the center is at least 70 million light-years. Meanwhile, the nearest edge of this cosmic void is located very close to the Earth, at a distance of about 3.2 million light-years. Due to this proximity, the local void occupies a significant part of our planet's night sky, about 40%. The main plane of the Milky Way containing many bright stars and large nebulae, covers the central part of this region from us. Still, its edges do remain accessible for observation. In 1854, a dwarf spiral galaxy was discovered a little north of the constellation Hercules. It was dubbed NGC 6503. Later, with the advancement of observation techniques, it became known that it is located in the middle of the local void, and its distinguishing feature is the incredible multicolor appearance. The spiral arms of the galaxy are permeated with bright red clots of heated hydrogen, and shining blue nebulae are stellar nurseries. The center is obscured by clouds of cool gas and dust, which have a noble brown color. NGC 6503 has a diameter of about 30,000 light-years, and its distance from Earth reaches 17 million light-years. Due to the gravitational pull of the Virgo supercluster, this galaxy is approaching us at a speed of about 43 kilometers per second. It is believed that its gradual approach to the local sheet will eventually saturate its space with interstellar hydrogen, causing an increase in star formation. It is estimated that in a few billion years' time, the current number of young stars could double, and the small galaxy will shine with renewed vigor. The motion of NGC 6503 is a clear demonstration of how the voids are likely to have come about. It is believed that the foundations of the large-scale structure of the universe were laid in the first minutes of its existence, at the time of chaotic mixing of matter and energy. Cosmic cataclysms of incredible power shook the young universe, forming local compactions and voids. Subsequently, clots of matter became proto-galactic clouds, and areas of space of reduced density became voids. Over time, the pervasive influence of gravity intensified this contrast, pulling stars and cosmic gas into relatively dense clusters, making the space and voids even more rarefied. Observations show that the vast majority of galaxies formed between 10 and 13 billion years ago. In addition, no significant differences have been found to exist between the age of galaxies located in voids and those that form global filaments. This fact also confirms the modern theory of the formation of the large-scale structure of the universe. Meanwhile, allowing for the cosmological expansion of space, we can assume that with time, the local void will become larger and more rarefied, and the Virgo supercluster will gradually disintegrate into several independent groups. At present, it is an association of about 30,000 galaxies concentrated in a region of space with a diameter of about 200 million light-years. At the same time, the total mass of the cluster is about 1.5 quadrillion solar masses, which is tantamount to about 1,000 galaxies such as the Milky Way. The Virgo supercluster is partially contiguous with two other galactic superclusters, the Centaurus and Pavo-Indus superclusters. At the same time, its other side borders on a vast region almost devoid of matter. It is called the Taurus void and is one of the largest known cosmic voids. It is rather difficult to study this part of outer space. The reason is that most of the void lies in the so-called zone of avoidance, a sector closed off from us by the Milky Way plane. The bright stars in our galaxy outshine the fainter and more distant sources, and interstellar matter absorbs and scatters their light. However, thanks to infrared studies, we do have some ideas about the structure of this void. The diameter of this tremendous void is about 200 million light-years, and the distance to the center is about 150 million light-years. When observing the void, one is immediately struck by the remarkably clear boundary between the relatively empty space and a bright cluster of galaxies located much further away. It is called the Perseus-Pisces supercluster and is one of the largest in this part of the universe. A transition this sharp is characteristic of dust clouds, even though infrared studies do not confirm their presence. In all probability, The clear boundary between the void and the supercluster is caused by gravitation, but the exact mechanism of their action still remains to be found out. Meanwhile, it is thought that the torus void, like most other cosmic voids, is not quite as empty as one might imagine. The way light passing through it is distorted suggests that this region may hide in its depths giant gas and dust clouds, the cradles of future galaxies. According to other hypotheses, huge masses of dark matter, the most mysterious substance in the universe, the properties of which are still not fully understood, may be contained inside the void. According to the most daring ideas, there are clots of antimatter or even more exotic matter with negative mass in the centers of cosmic voids. Nevertheless, despite their boldness, these hypotheses lie outside the boundaries of generally accepted scientific concepts, which makes it difficult to verify them experimentally. Currently, only 2 separate galaxies have been discovered tucked away in the space of the giant void. One of them, UGC 2627, has a spiral structure and resembles the Milky Way, while the second, known as UGC 2629, is an elliptical dwarf galaxy. Both objects are located almost in the heart of the void, at a distance of about 185 million light-years from us. The distance between them is small and is within a few 100,000 light-years. Perhaps there are other single galaxies hiding in the space there, but the Milky Way disk does not allow us to see them. Meanwhile, the Virgo supercluster, together with 4 other superclusters, forms a giant galactic filament called Laniakea. It contains more than 100,000 galaxies and stretches for more than 500 million light-years in space. Its gravitational center is the Great Attractor, a mysterious supercluster of galaxies located 250 million light-years from Earth. In its turn, Laniakea is part of a vast galactic stream, and further out, one can see that most of it is surrounded by a black abyss of unprecedented proportions. The light of distant galaxies is drowned in its emptiness, and even the mysterious and elusive neutrinos take billions of years to cross this cosmic abyss. To be honest, it is hard to believe that despite all the development of observational technology, such a gigantic void was noticed only 10 years ago. The year 2013. The University of Wisconsin-Madison. A team of astronomers led by Professor Amy Barger is working to determine the distance between galaxies. In the process, an unexpected and staggering fact is discovered. It turns out that Laniakea and most of its surrounding superclusters are enveloped by a cosmic void of unprecedented proportions. After making calculations, scientists discovered that its diameter exceeds that of any previously known void. The size of the discovered void turned out to be so enormous that several fundamental cosmological principles were questioned. It appears that the universe is much more elaborate than we imagined. The research done by Amy J. Barger, Ryan Keenan and Lennox Coey has led, in all likelihood, to one of the greatest astronomical discoveries of recent years. Their work has shown that our galaxy, along with its surroundings, is located in the middle of the largest supervoid known to science. It was named KBC, after the first letters of the discoverers' names. Observations show that the shape of the giant void is close to spherical, and its diameter may exceed 2 billion light-years. According to calculations, the Milky Way is located a few 100 million light-years from the conditional center of the Great Cosmic Abyss, and about the same distance from its edge. The discovery of a giant bubble of emptiness surrounding Laniakea helped to explain the paradox that had kept scientists busy for many years. The fact is that all galaxies in the universe are gradually floating apart due to cosmological expansion. Measuring the speed of this motion allows us to calculate the so-called Hubble constant, a fundamental physical constant characterizing the rate of expansion of space. However, if we take the galaxies closest to us to calculate the Hubble constant, it turns out that the rest of the universe is expanding too slowly. On the other hand, if we take distant objects as the basis, the Milky Way's surroundings are moving faster than they should. The discovery of the void has accounted for a lot. The fact is that the galaxies inside it, including the Milky Way and its neighbors, are constantly experiencing additional gravitational influence from objects outside the void. This creates an additional force that gradually stretches our cluster in different directions. It is also surprising that the KBC void is so huge that it comprises not only superclusters of galaxies, but also other voids. For example, the local void, as well as the torus void, are part of its structure. It turns out that compared to other voids, even though KBC looks large, it isn't quite so empty. Nevertheless, according to calculations, even this void is just a barely noticeable dark spot against the background of the observable part of the universe, the diameter of the latter reaching 92 billion light-years. If we look at the global map of the universe, we will see a lot of dark spots on it, close to the KBC void in terms of their size. Most of them easily fit within the framework of modern physical theories, while others show surprising and strange properties, difficult to explain from the point of view of science. And one of the most noticeable riddles of this kind in space is the Eridanus supervoid, also known as the CMB cold spot. It is estimated to have a diameter of 500 million to 1 billion light-years, and it lies at a distance of between 6 and 10 billion light-years from the Milky Way. This means that this formation is one of the most extensive elements of the large-scale structure of the universe. The void is located in the southern hemisphere of the Earth's sky and occupies an impressive area on it, several times larger than the full moon. However, it is impossible to see it with the naked eye. The CMB cold spot is visible only with the help of special telescopes that study the cosmos in the microwave spectrum. Thanks to these, astronomers have discovered that within the spot, relic CMB radiation of the universe is about 70 microkelvin colder than the metagalactic average. This deviation is nearly 4 times as intensive as the strongest anomaly previously recorded, and its gigantic size makes it a truly enigmatic object that requires extensive study. It is now believed that relic CMB radiation traveling through hundreds of millions of light-years of deep vacuum is gravitationally influenced by distant galactic superclusters. This causes the pervasive echo of the Big Bang to lose energy, making the CMB cold spot appear cooler in images than its surroundings. Nevertheless, this effect cannot fully explain the excessive cooling of relic radiation. According to calculations, the attraction of external galaxies can account for only a quarter of the observed deviation. It is assumed that the remaining 75% of the effect may be due to the impact of hypothetical dark matter or dark energy concentrated in the depths of the void. However, it is going to take a while before we can truly unravel this cosmic mystery. One flap of a butterfly's wing in Brazil would be enough to cause a hurricane in Indonesia. Edward Norton Lorenz. 1893. Kyoto, Japan. Young lawyer Henry Stimson and his wife Mabel White are on their honeymoon in Kyoto. The newlyweds are stunned by the colorful oriental city and its ancient history. They will remember this visit for the rest of their lives. May 11, 1945. Los Alamos, USA. A special US Army committee makes a list of priority targets for atomic bombings. Kyoto is top on the list as the largest industrial center in Japan. Pointing to the city's large cultural significance, the Minister of Defense Henry Stimson crosses it out from the list personally. This makes Hiroshima the main target for the US Army. Next in line at risk of bombing is the town of Kokura. August 9th, 1945, Japan. The crew of the US Air Force B-29 bomber is given a specially important order by the commanders. The military arsenal in Kokura must be razed to the ground. A state-of-the-art bomb, more powerful than any used before, is loaded on board the aircraft for the mission. However, the town is enveloped in a fog so thick that the crew cannot distinguish the target. The aircraft captain Charles Sweeney takes a decision to fly on, to the town of Nagasaki. Thus some sentimental reminiscences of 50 years back and an ordinary weather event affected the destinies of millions of people. And this story is just one of a great multitude of examples where seemingly small events may give rise to major consequences, incredible in their scale. This phenomenon is commonly perceived as the butterfly effect. But in reality, it is actually just a part of a big field of science known as chaos theory. In order to have a clearer insight into the correlation between small arthropods and destructive weather events, let's travel back to the recent past. In 1961, mathematician and meteorologist Edward Lorenz attempted to forecast the behavior of atmospheric flows by means of computer modeling. The scientist assumed that thanks to new computing capabilities, he would be able to predict the weather with an unprecedented accuracy. However, the results of the calculations baffled the scientist. In order to try to speed up the calculation process, Lorenz divided it into stages, so that the final results of the previous stage would be the starting conditions for the one coming next. Some of the resulting figures were slightly rounded up by the computer. This was so negligible that it was not supposed to have any significant impact on the final answer. Or so the scientist thought. However, in reality it turned out that the results of uninterrupted and stage-by-stage calculations differed dramatically. Later studies revealed that the system of equations Lorenz was trying to solve was inadequate for atmospheric processes modeling. Still, as is often the case in science, a misformulated task proved to be a step to an amazing and unexpected discovery. In his search for answers, the mathematician found that all possible solutions of the system group around two conventional positions which he dubbed attractors. If every solution were to be represented by a dot in a 3D coordinate system, they eventually form a shape reminiscent of a butterfly's wings. Interestingly, the slightest change of any initial parameter may sharply transfer the final calculation result from one wing to the other. In fact, Lorenz was not the first to discover an effect like that. Similar ideas were expressed by German philosopher Johann Fichte and French mathematician Henri Poincaré in their works. Be it as it may, it was Lorenz who transformed the annoying error of mathematical modeling into a potent and elaborate theory capable of offering answers to many questions. It goes without saying that hundreds of scientists would have contributed to the notion of chaos in the decades that followed, and the theory itself has come a long way. Its mechanisms can be applied to describe such complex phenomena and processes as turbulent flows, evolution of biological species, social interactions, and stock exchange quotes. The laws of chaos define the movement of celestial objects and explosions of stars, the birth of empires, and the demise of continents. And in order to get to the bottom of these factors and regularities, first and foremost, the notion of chaos has to be defined from the point of view of science. First of all, it should be noted that any chaotic structure is subject to rather rigid and clear physical laws, but they are so complex that the behavior of a system appears to be unpredictable. It is for a reason that structures like that are also known as deterministic chaos, with reference to their behavior being predefined. This is the principal feature that distinguishes them from stochastic systems, which are based on truly random events. If a chaotic system's behavior is supervised several times, the initial conditions being absolutely identical, it will react in the same manner. As for a structure based on pure chance, meanwhile, the result will never be the same. For example, experiments show that the decay of unstable nuclei in a sample of radioactive material occurs exclusively by chance. We can calculate the approximate number of atoms transforming within a specified period of time, but at the current stage of technological development, it is impossible to predict the precise time a given nucleus is supposed to decay. The exact mathematical definition of chaos sounds like this. A system has to exhibit nonlinear characteristics, be globally stable, but at the same time have at least one oscillating equilibrium point. At the same time, the system's fractal dimension must not be less than 1.5. It's quite a challenge to get one's head around this convoluted phrase, unless one is a professional mathematician, of course, rather than a layman. In simple words, it may be expressed by 3 principal points. Firstly, the system has to be nonlinear. Let's imagine we're influencing a structure in one way or another and getting a predictable feedback. It is logical to assume that after several interactions of this kind, the resulting change will equal the sum of all single ones. However, it isn't the case for a nonlinear system, and as a result, the structure will change more or less than we estimated. This was the effect encountered by Lorentz in his calculations, which prompted him to carry on with his studies. Secondly, a dynamic chaos system must be responsive to the initial conditions, that is, to exhibit this very butterfly effect. This means that no matter how tiny and almost completely negligible change of the initial conditions may be, it may force the system to develop in a completely different manner. Thirdly, as a system develops, its separate parts are supposed to overlap and interact with each other. Such interactions are usually not taken into account in classical physics. However, quite often it proves to be a grave omission. It is keeping track of multifaceted influence that makes chaos theory models so elaborate and so like real structures. Let's think 13.8 billion years back. Just a few quanta of time would have elapsed since the occurrence of the hypothetical Big Bang. There is neither matter nor energy around us as we know them, and the 4 fundamental interactions are interconnected by one bizarre force. The physical laws known to us are not yet applicable at this point. However, other ones are working instead, which are just as rigid and which predefine the system's future development. At the same time, a tiniest change in any point of the germinating universe is capable of changing its future completely, whatever the reason for this tiny change. It appears that our reality was literally born actually thanks to chaos, in the scientific sense of the word. Now let's imagine what it's like about 1 million years later. The space of that time would have become more like what we know it to be, although there aren't any stars or planets around. There are only countless clouds of primary hydrogen floating around the young universe. The hydrogen is exposed to gravity forces pressure. This forms gravity centers, which are soon to become the first stars. These gas clusters are splashed about quite irregularly, with no system to speak of. They are also massive enough to mutually exert gravitational influence. At the same time, with any of the protostars moved aside, or with its mass slightly altered, these changes will influence not only its own evolution, but that of its immediate neighbors as well. This means that the laws of chaos continue to rule the universe. In the course of billions of years that followed, primary stars burned out and exploded, saturating the universe with heavy elements. New stars were born from clusters of hydrogen, with clouds of cosmic dust near them swirling in gigantic vortices and forming protoplanetary disks. It is easy to see the already familiar patterns of chaotic movement and interaction in their structure. And this is how 4.5 billion years ago the solar system was born. Our eyes can perceive only a small part of the amazing multicolored nature of the universe. Meanwhile, some dimensions of the cosmos are revealed only beyond the limits of visible light, and it is only through observation technology that we are able to touch this astonishing beauty. Every second, hundreds of telescopes are watching the universe, which means that every moment we take one more step towards new knowledge and discoveries. And let's keep in touch.